Hello, here we have a very interesting setup to allow us to study what is called nuclear magnetic resonance. And we are going to look at NMR in the Earth magnetic field without need for a large superconducting magnet. So here is the setup. We have a bottle of water. This is deionized water. It has a lot of protons in it. There are 110 moles of proton spins for 1 liter of water. So when you put this in the solenoid coil, and then if we energize the coil to apply a magnetic field to this water bottle, the nuclear spins will be aligned along the applied magnetic field, which is this way. And then when you turn off that magnetic field, the nuclear spins will be not in vacuum. It is going to be under the effect of the Earth magnetic field. And the Earth's magnetic field is pointing perpendicular to that polarizing field we just turned off. Let's take a look at the coil setup. The solenoid is here. The water bottle is here. We polarize along the length of the solenoid. When you turn it off, the water proton spins will be experiencing the Earth magnetic field that is approximately perpendicular to the polarizing field. That means those spins will precess around the Earth's magnetic field. So it's going to precess like this. Then the same coil that we were using to polarize the spins now function as a detector of the precessing nuclear spins, and we can observe that on an oscilloscope. So let's take a look. Here is the electronics part of it. We're supposed to apply up to 30 volts here. It's available from that power supply. Take a look. And what this box does is when I press this button, it has 3 seconds here. It will count down to 0. In this time, the voltage that we set up will be applied to the polarizing coil. It will apply a few amps of current to polarize the spins, and then it releases it. And once it turns off the polarizing field, as I explained, the nuclear spins will precess around the Earth magnetic field, and that gives you a signal at about 2.7 kilohertz. So let's see what happens if I press this. There's countdown. And then you see that the oscilloscope shows some sign of signal that goes down like this, but unfortunately it's very short-lived. You don't really see much beyond a few tens of milliseconds. We try it again. Look at the oscilloscope. So that's a precession signal, but it is too short. So what we can do is to apply a technique called spin echo. The reason why the signal is so short here is because the water bottle we saw is experiencing a non-uniform magnetic field. The Earth magnetic field is uniform, but this room has many sources of inhomogeneous magnetic fields. So the water bottle is not really experiencing a single frequency. It is precessing in the distribution of frequencies, and that makes the signal live shorter. So what we do is we use a function generator here that is available to generate a short pulse to invert the spins after the signal apparently decayed away. Then the spins will rephase at a later time to form a signal that can be visible on the oscilloscope much more clearly than without the spin echo. So in order to do that, we have to sort of manually apply the pulse just in time to catch the signal. So let's see if we can be successful. What we do is we press this button so that the countdown happens and the spin precession occurs when this is 0. And immediately after that, we trigger this generator so that it applies 180-degree spin flip pulse, and then the oscilloscope is supposed to catch the signal when the spin echo is formed. So let's see if we can do this. I hope you saw that. So there was the initial signal that decayed away fast, and then you apply the 180-degree pulse that shows up here. This is not the NMR signal, this is the electronics artifact. But later you see a signal that appears here, which is coming from the nuclear spins in the water, and this is the spin echo. And we see that the echo time in this case is from here to there, that's about 400 milliseconds. Let's try it again. Countdown. Trigger. Now the 180 pulse was a little late, so we see that the echo is forming there, but it is appearing at a later time. So anyway, this shows that our signal decaying away here was due to inhomogeneous magnetic field, and if we apply the spin echo, the signal can be revived at a later time, and this allows you to detect the spin precession signal even in the presence of strong magnetic field gradient.